are you?
Oh, thanks.
Okay. So let's start. Equation. Okay. So since this is a let's say kind of mini course on Hodge locus, at the end of the day I will need the moduli space that I will introduce in the end of my talk. And really the BCO will not pop up in our concept. But let's, this is one of the origins of this new moduli space that I'm going to make propaganda of it. Okay, so let's start default. Since the invention of mirror symmetry, the people are interested in generating function of group of Witten invariant of X check, and this is something like at the end of the moduli space X check beta virtual this way. So when you fix the genus 1, 2, 0, 1, 2, beta in H2 X check Z. This is basically, from the mathematical point of view, counting curves on its check with the homotopy class beta, and then Fg Ng beta Q. And after many efforts in mathematics, we know we can define these objects concretely. So let's maybe I will focus in my main example, which would be quintic, or the quintic H2 X check Z is one dimensional. So at the end of the day, this guy will be and then you choose a generator for H2X check, and this will be, I will write it, instead of beta, you can put it D. N, G, E, Q, the D equals 1. Okay, this is a kind of enumerative algebraic geometry going on. I will not focus on this topic, but the point is that mirror symmetry tells us how to compute this kind of objects from completely different point of view, and the main focus is this. So maybe I tell. So the main references are book that I wrote. It is called. It's published. 2070 by International Press, and then also my work with what's the order of the Moral Alim, me, this is a story for General Talabiel, but I will talk about this book, which is the case of just quintic and mirror. Okay, so as I was saying, then mirror symmetry tells us how to handle these generating functions. And at the end of the day, for me, mirror symmetry is a kind of elephant in the darkness. Everybody touches a piece of the elephant and has his own impression what mirror symmetry is. But so this is, I will tell the part of the elephant that I understand what it is. So the mirror symmetry has A model. So this is actually the A model. Then there is a B model. For the B model, one introduce a paradical mirror quintic, 0, 1. So it's a kind of between any two different type of Calabi varieties. But as I said, I will focus on the example of quintic, which will be the A model and its mirror quintic. And okay, so maybe I think it will not make sense really that I put the definition of the mirror quintic, but maybe I put just some basic data of the mirror quintic. So it's Hodge diamond, maybe like I put just its Hodge diamond. So these are the sum of this is dimension of the h. There are x. This is the h to the round of x. So these are the height numbers are 1, 1, 1. And one appearance of the one manifestation of the mirror symmetry is that the quintic has the same Hodge diamond if you rotate it 90 degree, whatever state you want. So and at the end of the mirror symmetry tells us how to do a kind of complex geometry with mirror quintic and get information about this FG. And at the end of the day, you start counting, creating this number, but really without counting. You're just doing some complex analysis. And for me, this is a kind of the miracle of mirror symmetry. Okay, so let's try to do. But let me say, if you look in the books, at the end of the day, the mirror is introduced in this way. You take this dwarf family. 1, 2, 5, 5, minus c, x0, x1, x5. You take its projectivization, and then there is a discrete group acting on this variety. Then you make the quotient. The quotient has singularities, and then you take this and the resolution, and then you will land on the variety with such numbers. But practically, this description is kind of nobody uses it because at the end you will need the periods of its periods, and its period you can just handle it just knowing this equation. Okay, so the basic idea is that I want to slowly say what is of mirror symmetry teaches us to compute this the generating functions, of course, up to some ambiguity. And maybe I have to tell that at the end of the day, okay, this I will show you some result of some computation, but at the end of the day, these are these are adaptation of some computation done after PCOV article by Yamaguchi and Dion, and then the version that I could produce. Okay, so let's see how the things works. First of all, as I said, in the B side, you do just complex geometry, periods, and this kind of stuff. So the round homology of mirror quintic is of dimension 4. So I will need 4 differential forms, and I will integrate them over 4 cycles. So that's omega 0. Maybe I make this my notation. Omega 1 holomorphic. But I will put just maybe some how some formulas look like, but for the precise formulas, I think you might have look at this article. So the first basic ingredient of this Nicolabia variety has holomorphic 3 form. And as I said, in order, but not periods of this thing is enough, but we will need, as I said, the Dirac homology dimension 3. One needs full basis of the Dirac homology. So what one does, omega I. One also introduce this omega I, which will be beta I minus 1, omega 1, and then I equal to 1, 2, 3, 4. What is theta? The mirror quintic is its moduli space of dimension 1. So basically, this P1 minus 3 points, the z coordinates is the classified as mirror quintic. Okay, so you have this derivation, and there is the way to differentiate differential forms. And the modern way to say what is this differentiation is that and by this operation I will get 4 differential forms, and it is easy to see that this omega 1, omega 2, omega 3, omega 4 form the basis of H around XC, removing these 3 points, and then I will choose delta 1, delta 2, delta 3, delta 4, H3 XC, C3 homology class, a symplectic basis. At the end of the day, what this means, this intersection matrix is just this I2 times 2 minus I2 times 2, 0, 0 matrix. And in order to introduce the computation, what I need, then I will need this period matrix. Period matrix. Then what? So I have 4 differential forms. I integrate over 4 cycles. So this will be omega j delta I ij 1, 2, 3, 4. At the end of the day, I have 16 periods. And as I promised, if we are not used to this abstract notion of differentiating differential forms, then you can think of this, let's say omega j was theta j minus 1 this omega 1. So what is this? Then, so at the end of the day, since you are in families, maybe I have to make a picture. So since this mirror quantic is the third homology of dimension 4, I can, let's just make intuition. That's a kind of Riemann surface with of genus 2. It is, at the end, it's a 6-dimensional object, but I'm not just for the sake of intuition. So maybe let's delta 1, and if you call it xc. And at the end of the day, this delta iso depends on z. There are families of cycles moving depending on z, and delta. That here I have not put the letter z, but at the end of the day, what this is just the differentiation of what of this integral. This is going to be holomorphic in z, and then you are making the derivations of this holomorphic function in z. Okay, so I will need this 16 periods. So maybe I have to tell, and this z equal to 0, it's called maximal unipotent monochrome point. And again, one of the things that mirror symmetry tells us you are not supposed to take any basis, but the choices of this symplectic spaces is done in such a way that so this omega 1 is the holomorphic Trig-Zero form, omega 1 delta. So this in my choices I will do it this way. This will be holomorphic in T. Omega 1 delta 1 will be ln as z something something. All these something are holomorphic, and then maybe I write the full omega delta 3 is ln as z to the 2 something ln as z something something, and as I said, I will not order one of the other period. At the end, all these things means a holomorphic. So this means that around the z equal to 0, we have this pattern of periods. One is holomorphic, the other one is logarithmic. The third one is double logarithmic, and actually the fourth one is triple logarithmic. Okay, as I said, I'm going to put just output of the computation, and okay, so elements constructed from periods. Okay, so before I want to put some statement about G, but I need some special combination of all this xig. So I will now use this my xig notation. So again, the exact formula you can have a look in the book. But the point is that okay, maybe what I can do so it will be. Okay, before writing some examples of this, maybe first I have to put meter. So something also that mirror symmetry tells us that you have to define a map. This is called the mirror map. This Q variable, which at the end of the day will be this q variable here. What will be this q variable? You will define it as t e to the 2 pi I x11 logarithmic period, x21 holomorphic period. So logarithmic, so this was just exactly this one, and then this was x1. Logarithmic period, holomorphic period. Okay, now I'm going to write samples of these quantities in terms of xij. But okay, but maybe let me first write down the output. As I said, this is a kind of many computations done by Yamaguchi-Yao and by me in my book. Is that I don't know? Let's put it like a proposition. Okay. So I will write something here. Then, so F1, okay. So the genus one, generating functions of Gromov-Witten invariant, it is Ln T4, 25, 12, T4 minus T0 to the 5 minus 5, 12, T5, 1 hour. And for G bigger than 2, okay, FG, okay, maybe I can write here, and then I explain a little bit what's going on. FG has this structure. So QG T0, T1, T6, T4 minus T0 to the 5, 2G minus 2, T5, 3G minus 3, where QG is the homogeneous polynomial of degree 69 G minus 1 with considering the weights for the i's, so the weights will be 3i plus 1, I equal to 0, 1, 4, degree T5 is 11, degree T6 is 8. Okay, so let's explain what is going on. So, as I said, mirror symmetry, and then Yamaguchi-Yao, and then it's just a holomorphic period. The order's expressions are a little bit ugly. I will not write it. Maybe I will write a T4. T4 is Z, the holomorphic period to the 5. And let's say T1. And the other expressions also you can find in the book. Maybe I write also T5. T5 is something like 5 to the some constant, Z minus 1, X to 1, X1, 2, X2, 1, it's a kind of Wronskian, X1, 1, X2, 2. So, okay. So there are seven expressions, polynomial expression in terms of period you can define, such that what happens? All of them, maybe all of them is equal to 0. The point is that all these periods in z equal to 0, some of them they have logarithmic. So all these 7 expressions, even some of xij, they have a logarithmic, but because of the combinations of xij that it is taken in these formulas, the logarithm will disappear. So at the end of the day, all of them are holomorphic in z equal to 0. And the point is that this Q, the mirror map that a mirror symmetry tells us to define, it is a new coordinate in C around 0. So at the end of the day, you have seven quantities in Z. Now change your coordinates to Q. You will get 7 Q expansions. And so the mirror symmetry will tell that this Fg has this polynomial structure in the denominator, and this in the denominator there is this one. So all these Ti's will become Q expansions with some coefficients, nonsense coefficients. But if you make this guy, you compute this Q expansions of this guy, and then you will get the Gromov-Witten invariance of the A set. And for example, let me say, open problem, prove the same thing. State in the if you are enumerative algebraic geometry, then you say, okay, understand what is Fg. So this kind of conjecture says that there are 7 Q expansions that any Fg can be written in terms of these 7 Q expansions. For this 7 Q expansion, for their coefficients, apparently there is no meaning, because we only know what is the meaning of the coefficients of this Fg, but at the end of the day, let me say, this will, for example, this will also imply that the field generated by this Fg, its transcendental degree is at most 7, which is kind of still open question in the A side. Okay, but as I said, this is a kind of mirror symmetry, so whatever we are doing here is a kind of dictated by us by, let's say, physics manipulations. So, okay. Any question? Okay, so maybe I can also again some other computation done by Yamaguchi and me, and then I try to make a kind of algebraic geometry out of this. For now, I'm just telling the output of the computations, and there is why, for example, these expressions in terms of periods, why I am taking, it's not clear why it works. Okay. Maybe, okay, so maybe I'll tell also this COV equation. Again, the origin of this COV equation is a kind of using periods and the holomorphic periods and so on. Again, the output of the translation from the original one to the one which Yamaguchi introduced, and then to this Ti's coordinate that I introduced, it will be something like this. Okay, so So I will just tell we can introduce 7 derivations in derivation, but I will use a geometric language for derivation. It will be vector field in T0, T1, T2, T6. So these derivations or vector field, they are the basic ingredients of the Pizzioli anomaly equation. Again, I will write just a sample of this vector field. For example, and then after this, I will try to formulate the things in a more conceptual way. So the first derivation is basically key dq. But the point that this vector field can be translated as a derivation in Ti, and it will have some ugly expression in terms of T0 that I don't even dare to write it. T1 here, rational functions in Ti's. Maybe some of them that at least I can write it. For example, this R1 is a very simple one. T5, T5 plus T6, T6. Maybe the one that also the R2 also I can write it. T0, T0 plus 2T1. The most simplest one are this one. I will write R4 also. 6 to 5. So, R4, R0, R1 until R6. At the end of the, okay, I'm again trying to explain the output of the many computations. But what is, so, as I said, one output is this polynomial or rational function string, rational function structure of this FGs, and okay, so the this PCOV is basically this kind of this class of equation. So once you have a derivations in TIs and rational functions in TIs, then you can make a derivation. Okay, so for example, and at the end we have this kind of differential equation. Li(Fij) equal to 0, 1, 2. Here, 2 Fg is a kind of 2G minus 2 Fg. And maybe the most important piece of the derivation that for this reason I wrote R4 explicitly, the derivation of this Fg with respect to R4 is 1/2 R0 to the 2 Fg minus 1 plus R equal to 1, G minus 1, R0, Fr, R0, Fg minus R. And yeah. So maybe I have to recall that the vector field function, this for me is df, which is a differential form, acting on the vector field and then again getting a function. Okay, so maybe this is the most important piece of this anomaly equation. So this is a kind of recursively computing FG. If you make this derivation of FG with respect to T6, and then you have to multiply it with this guy, then this will be the derivation of previous Fi's. And with respect to R0, which is the holomorphic context, is basically like this one. But as I said, you can write it in terms of Ti. And this one, completely open. Well, as far as I know, there are some efforts to reproduce this one in the A side. This means that if you are doing an numerical algebraic geometry, at the end you want to invent a kind of recursion for FGs, but for me, so far, it's a completely open question. Okay. So far I said that whatever we are counting in for A side Calabi-Yau variety, this genus G chromophyton invariant, they have this FG function structure, and also they satisfy this kind of differential equation. So the rest of my talk, what I'm going to do, there is some moduli space going behind all these computations, and this is a more conceptual object. All these things are obtained after these manipulations on such a moduli space. And I'm going to explain a little bit about this. Any questions? You have a time? I don't know.
Is 211.
Okay. So maybe then, and this is the basic idea of that I want to take to other seminars. The concept of the moduli space. Okay, so what is this moduli space? Let's go X mirror quantic. So, as I mentioned before, it is only that the mirror quantic is of dimension 1, and its moduli space is dimension 1. So, and what we are going to do, okay, maybe I put with the ingredients. So, H3. So, this is its moduli of dimension 1. This guy is of dimension 4. 1 plus 1, 1 plus 4 times 1. And the point is that I will need something called the Hodge filtration on this guy. Okay, and that I said this can be done also for any Calabi-Yau variety. But for simplicity, I will stay in the case of mirror quantic. F4 0. So for example, what is this? So you in the complex context, we know that this has this Hodge decomposition. H1, H1, 2, H03. And Hodge decomposition is typical to complex geometry. You cannot really reproduce it in purely algebraic context. But something that you can produce it in algebraic context is the concept of Hodge filtration. This is, let's say, F3. Then the sum from here to here, call it F2. From here to here, call it F1. And then the full F0. So the dimensions, here it is 4, this is 3, this is 2, this is 1. So in order to make a kind of conceptual interpretation of all these manipulations coming from physics, I will need the Hodge filtration. I will need the cup product in the round homology, which will be this pairing alpha omega going to alpha wedge omega. And one of the reasons why I am putting this 2 pi I3, because when you insert this 2 pi I3, everything can be defined over arbitrary field. You don't need to work over just complex number. You can also work over mirror quintic or any kind of variety over arbitrary field. So I will need this one. So, I think already done. So, this new moduli space that I am talking is the moduli of Calabi-Yau variety, in our case mirror quintic, and a basis, a full basis of alpha I, a basis of H3 the RAM, and this will so there will be compatibility with the Hodge filtration. What this means that this guy is a basis of F3, these together is a matrix of F2, and these three bases of F1. And something also very important, there must be some conditions with respect to this pairing. Maybe let's call this one right in this way. We know that this pairing is non-degenerate. Some also condition that I will put. So in the spaces, when I make the matrix of this pairing, this is a 4 times 4 matrix. So at the end, I will ask that this 4 times 4 matrix, it is of this type. Everywhere 0. And so what we are doing, we are enhancing our Calabi-Yau variety with a full basis of its de Rham homology, such that this basis has some compatibility with the Hodge filtration, and with respect to cup product, it's also a kind of a constant. It doesn't depend on X. So as I said before, the moduli of X is of dimension 1. Now we are adding this object. When since you are adding elements in the Rham homology, the dimension will increase, and it's a kind of simple exercise in linear algebra. Something that you will notice, the dimension of this guy is of 7. One dimension comes from the moduli of X, and another 6 dimension comes from the freedom of choosing of the spaces. So you don't have the full freedom of choosing a basis because of these two conditions, but still there are 6 dimensions which this alpha 1, alpha 4 can move, and then you will observe that this is of dimension of 7, and this is the same 7 that I was explaining in the beginning. This a lot of manipulations of periods and so on, and they slowly. The idea is that this is the heart of all these period manipulations in B side of mirror symmetry, and okay. So let's. Okay, so as I said, the classical moduli of x, it had this coordinate p1. It is just this p1, 0, 1, infinity, and then and its coordinate we called it by z. So one can start trying to construct this moduli space, and again after many manipulations, when you want to really construct this moduli space, it's a kind of construction of moduli space not using GIT or the sophisticated machineries in algebraic geometry. It is a kind of construction by hand to the time when Hilbert was trying to understand this geometric invariant theory. But when you start to construct this T, then you will see that it's a affine variety. Since I started to do everything over complex number, maybe then I put C here, but actually you can also put Q if you start talking about Calabian variety, the round homology, everything defined over Q. But at the end of the day, this will be, you will see that it is the spectrum of a polynomial ring in 7 variables, and then you have some discriminant that you have to invert. T5, T4 to the T0 to the 5, and then some. Okay. As I said, there are now I am announcing the output of some computation in an attempt to construct this moduli space that it has nothing to do with period. It's a kind of just polynomial or commutative algebra. And originally, this TIs I invented in this way. I mean, the first one construct is moduli spaces. And then maybe I have to say this kind of this discriminant stuff here. Okay, so this, before this one, there is an algebraic. Okay, so the moduli space consists of the Calabian variety and the basis of the round homology, but you can make the change, base change, you know. And there is, you can write an explicit maybe I can write it. So the point is that you can write an algebraic group formed by 4 times 4 matrices. G. Let's say G 4 times 4 matrix. So what? Let's just say lower upper triangular, and then another condition. If I call this matrix phi, then G transpose equal to phi. It turns out that this G acts on T, and this action is in the pointwise version, it is just a base change. So it's a kind of G and then X and alpha. Maybe I write alpha as a 1 times 4 matrix. So the action will be, this will go to X and G alpha G. So the fact that it's upper triangular will guarantee that it keeps the Hodge filtration invariant, and this will guarantee that it keeps this product invariant. So there will be a group action on this moduli space. And okay, so what else I need? And it turns out that when you make the quotient, this is the same classical moduli space, because the making the quotient, it means that I am forgetting this additional structure that I put on my Calabi-Yau. So this would be just the classical P1 minus 0. Actually, I have to say that 0 and 1, because the Calabi-Yau at infinity, it is also a smooth Calabi-Yau, but because of some extra automorphism that this is smooth Calabi-Yau, it has sometimes it is useful to also remove this one. But at the end, it will be just this will be P1 minus 0, 1. So essentially, there is two singular Calabi-Yau varieties, one over 0 and the other 1. Okay. What else? Okay, then maybe okay. So then something also we will observe. There is a universal family over T. So usually in algebraic geometry, the moduli spaces, you cannot expect that the universal family exists, but because of this enhancement, you will observe that that universal family exists. And what else? Then you have to, when you have a family of varieties, you have the notion of the Gauss-Vannin connection. So it will be a connection of the cohomology bundle of this guy. Maybe I am gonna. So let's say this object is a complex of the cohomology bundle. So this cohomology bundle comes with a natural connection called Gauss-Vannin connection, and okay. So what I will justify the derivations that I wrote in for the BCOV anomaly equation. They are vector fields in when you interpret vector fields in T. Okay. Then something that you will you prove it. There is a unique. So the derivation now for me will have the name vector field. So this will be R0 in T. Such that something that you can make with this the Gauss-Vannin connection, with any connection. If you have a connection, then if you have a vector field, you can compose the differential forms here with the vector fields. At the end of the day, what you will get a map from a homology bundle to itself, and since this T moduli space comes from the choice of alpha 1, alpha 2, alpha 4, these cohomology bundles this cohomology bundle has global sections called, I will call it again alpha 1, alpha 3, alpha 4. And then when you composite this vector field R0, then you will see that it has this particular format. So this for some unknown quantity that you don't know. At the end of the day, these are the key, du key, or the or its TI expression that I didn't write, will be characterized by this fact that its composition with the Gauss-Money connection has a very special format of matrix, and the other vector fields which pops up in BCOV Anoman equation and are interpreted in this geometric quadrant in this way. So you have G acting on T. So if you can form the Lie G and the Lie algebra of G. For any element of the Lie algebra, you can get a vector field fundamental vector field attached to G. Okay, so it is a kind of a classical construction differential geometry. Whenever a group acting on some space, any element G and the Lie algebra will give you a canonical vector field. This is called fundamental vector field. This dimension of dg or G is 6. So you choose 6 generators of this type. This Lie G, and then when you want to compute the corresponding fundamental vector field, you will land at R1, R2, R6. This vector field that I was writing, and so okay, maybe I try to finish it. And so there is a kind of translation of all this FG. So let me say in this way. So all these topological these FGs will be translated as functions in this regular functions on this moduli space, and then the derivation involved in BCOV equation you will get in this way, and everything will reduce some computation on this bigger moduli space. So maybe if you want more details, as I said, all the computations are done in my book. But the main idea of this talk that later I will use this concept of the moduli space, which it turns out to be useful even if you want to do something beyond this physics application. I mean. For example, I will introduce this bigger moduli space in Calabi of fourfold in order to study something called the Hodge locus, which is the main focus of this series of things. Okay, thank you. That's finished. Any question? Okay, then.